Hello everyone. We are group 9 and today we are going to talk about Suffix. Before we start, I will introduce my group, my team. I'm Lê Quốc Cường and my partner here is Thanh Hữu, Khánh Bình and Chí Bảo. Let's start with the first session is motivation and definition. We will explain why suffix were invented and what they define. Let's talk about the grocery list problem in the motivation. Let's assume you go to the supermarket with your grocery list on hand. Then you wonder whether banana milk is in your list or not, and then checking letter by letter would be very time consuming and slow, and we need and that's a problem, and we need a better methods. So let's analyze the problem. So what makes our grocery list problem so slow? Without a better method, we have to read through each word letter by letter. That's like reading meals, then eggs, then cheese, before moving to the next item. With many items like this, to check this is very take time and make really slow. But what if we organize our list differently? This is where Suffix help. This is like a special version of your list that lets you find any item faster, no matter how your list is. And what a suffix tree is? A suffix tree is a tree that contains one suffix of a particular string. For example, a string S with length M would have the following property. The first is rooted directed tree with M leaf, and second, its X is labeled with a string, and the third is its X label from a node begin with a unique character, and finally, for any leaf, the concatenation of the X label would spell out a suffix. You can see the example of suffix tree on the right hand side is the suffix tree of the string bananas. You can see that the root is bananas, and that's stored on suffix of the string bananas, like nanas, ananas, and so on. And this smart arrangement is why finding any part of a string become super fast. And in the next session, we will discover more about the suffix tree.
We continue with part 2, which is the construction of a suffix tree. First, to construct a suffix tree, you need to understand some concepts. The first concept that we need to understand is implicit suffix tree. An implicit suffix tree, otherwise known as modified suffix tree, is a suffix tree with these modifications. First is the removal of all terminating characters. Here is the dollar sign. The removal of all edges that doesn't have label, and last but not least is the removal of all nodes that doesn't have at least 2 children. For example, this is the complete suffix tree of ABCA. And its implicit suffix tree is very simple. It's just like this. Implicit suffix tree are used to represent intermediate states of the tree, since the suffix tree would be built one character at a time. Next is the active point. The active point is a triple of 3 variables. First is the active node, second is the active edge, and lastly is the active length. The active point shows us where we need to insert our current suffix. The active node is the root node of the edge where we are inserting. The active edge is the edge that we are inserting. And the active length is the position that we have to go from the active node on that active edge to reach the position that we want to insert. For example, in this tree, if the active point is root A1, we would follow the root along the edge with the letter A at the beginning, and we go one character. So the active point is on the A edge, particularly after the first character, which is where the arrow is pointing at. Next is the remainder and the suffix length. The remainder is an integer indicating how many new suffix we still need to insert. When we add in a new character into a string, the remainder would be incremented, which signifies that there is an additional suffix that needs to be added. Why? Because the final character itself is a new suffix. And when a suffix is successfully added to the tree, the remainder would be decremented. There is also the suffix length, but it will be explained a little bit later. Now we go into the general description of the Ukonen's algorithm, which is the algorithm that will build the suffix tree for us in linear time. Ukonen's algorithm constructs the implicit suffix tree for a string with length n by recursively constructing the implicit suffix string implicit suffix tree for the string before it from 0 to n-1, and then extend it into the implicit suffix string of s by adding the final character. For example, if you want to construct a implicit suffix tree for a string with 4 characters, you would first have to construct the implicit suffix tree for the string with 3 characters and then add in the last character. As such, at any given time, the algorithm builds the suffix tree for the characters it has seen so far. That is why it has the online property. It is divided into n steps, each step for a character. And the suffix extension is all about adding the next character into the IST build so far. To handle this extension, Ukonen's, the professor, the computer scientist that created this algorithm, created 3 extension rules. The first rule, after we insert from the root, the active length is greater than 1, then we do not change the active node, we decrement the active length, and the active edge is shifted to the right. Rule number 2. If we split an edge and we insert a new node, and that was not the first node created during the current step, we connect the previously inserted node and the new node through a special pointer called a suffix link. A suffix link is a link between the first internal node and the second internal node. This is also the link between the second and the third internal node created during the same step. You will understand why we need this later. And rule number 3 is after splitting an edge from an active node, that is an internal node, we would follow the suffix link going out of that node if there is any node, any suffix link, and we set the active node to the node that at the end of the suffix link. So basically, the suffix link acts as a highway from a node to another node, so that we can move to the position that we want to insert easily. If there is no suffix link, which is there is no highway, we just go back to the root. This only can consider the active node, so the active edge and the active length remain unchanged in the process. And that's all. That is 3 rules for the Ukonen's algorithm. Okay, a little bit complicated, I know, but let us go to the demo. You understand? If you don't understand the algorithm right now, it's okay. You just concentrate on the demo and you'll get it. Let's first demonstrate the construction of a suffix tree that is very simple, with only 3 characters, A, B, and C. We build the suffix tree step by step. So first, we will create the suffix tree for the first character, A. We insert A into the root node, and we label it at 0 hash. Hash is currently 0. So this is the root node, and it points to a leaf node, and the value of that edge, or basically that is actually the value of that node, is 0 hash, and it is A, because hash is now 0. So 0, 0 is basically the first character of that string, which is A. Next, we go to position 1. So hash is now updated to 1. To insert the new suffixes, we first expand A to AB and insert 1 new edge for B. So 0 hash stay the same because hash is now updated to 1. So 0, 1 is AB, and 1, 1 is now B. This is a new edge that we created for B. So from A, we go to AB, and B is a new leaf node that we just created. Okay, I think you know where this is going. Step 3, we add in the C. We increment the position, which is the hash, again, and update the tree by appending C to every existing edge. The act of incrementing the position is updating the tree because it will change every edge to its new edge, which will have the C in it. So AB now becomes ABC, B now becomes BC, and we add in the new edge for C, which is the third edge over here. So we have three edges, A, B, C, B, C, and C, and that's it. We've constructed the implicit suffix tree for ABC. Hooray! Very easy, I know. But we have some observation. First, there are as many steps as there are characters. Second, the amount of work in each step is basically all one because all existing edges are updated automatically by incrementing the position and by inserting one new edge for the final character, which is we are done with the step. So each step can be done in all one time. The edge representation for ABC is the same as it used to be in the initial tree. So the only thing that changed was the value of the hash. Changing the value of the hash automatically change all of the leaf edge to the desired position that we are in. The only thing that we need to add in at the end of the day is the character, the last character itself. But this is simple because this is a very easy string. ABC did not contain any repetition. With a more realistic string, things get much harder. We look at a more realistic string like ABC, ABX, ABCD. It starts with ABC, but AB is repeat and then followed by X, and then ABC is repeated again and followed by D. The first three steps are exactly the same. We would get this tree right here. But the fourth step is adding A. Moving the hash to 4 updates of the edge to that. And we need to insert the suffix of the current step, A, at the root. But unlike previous steps, we notice that there is already an edge starting with A. So this is what we're going to do. We do not insert a new edge at the root node. We just notice that A is already in the tree. So we basically do nothing. But we need to remember that there is a suffix that ends in the middle of that edge. So we would set the active point to root A1. Basically after the A. And the remainder is 1 because we haven't added in the A yet. So at the beginning of the next step, it will be 2 because we don't decrement the remainder. we haven't truly added in the suffix a, so it is still there, so it will remain there. Okay, that's all for step 4. We go to step 5. We update again the position to 5. This automatically updates the tree to this, basically adding B to every leaf edge. Since it is the start of a new step, remainder is now decremented to 2. But that is our problem. We have to add in AB and B in the current position. We realize that B, where we need to add at the active point right now, is already there next to the active point. So again, we do not change the tree. Instead, we update the active point to root A2. So we're incrementing the active length. The remainder in this step will also not decrement itself. So at the next step, it would be 3 because we haven't inserted the 2 final suffixes properly. Step 6, we increment the position to 6. So the tree is now this. The remainder is 3. So we have to insert ABX, BX, and X. First, we insert ABX. The active point already shows us where we need to insert the X to make the suffix ABX in the tree. This time, we don't see any X next to the active point. So, when adding the X, it would split the tree into an internal node at the active point, turning the tree into this tree. And as we have inserted ABX from the root, according to root 1, the active edge is now updated to the next character, which is B, and the active length is decremented from 2 to 1. So the active point moves from AB to B right here. The story continues, and we add in another X at the active point because the remainder is still 2. We still need to do more work, right? Adding in the X split the edge for a second time. So checking rule 2, we need to connect the previously inserted node to the new node with a pointer, which is a suffix link. In the diagram, it is the arrow, the yellow arrow that is dash, the dash yellow arrow. Applying root 1 again, the active point is now root x0 because the next character after B is X, and then the active length is decremented from 1 to 0. Root x0 and the remainder is 1 signifies that we need to insert a new edge X at the root because we don't see any X appearing in the original edge from the root. And that's it. That is step 6. Next, step 7. Step 7 is where we increment the position to 7. So we attempt to insert the new final character, which is A, to the active point, and see that it is already there. So we update the active point, like usual. And then, step 8, we try to insert B and realize B is also next to the active point. So we update the active point again and increment the remainder. But this time something special happened. The active point is at the end of an edge. So now we need to reset it to the node at the end of that edge is pointing to. We call this node 1. Node 1 is the internal node that AB ends at. So the active point is reset to, the active node is reset to node 1. The active length is reset to 0. And the active edge is reset to no. So no character. Continue. Step 9. As usual, we increment the position. We try to insert the C. We notice that C is already there next to the active node. So we update the active point to node 1 C1 and increment the remainder. We just see that we are stepping through the step without actually adding in the suffix. So step 10, we will add in all of the suffixes. Incrementing step 10, the remainder is 4. So we need to insert 4 suffixes at this node, at this point in time. We add in the D at the suffix point, at the active point. We don't see any D next to it. So it will cause a split. And remember to decrement the remainder to 3. And according to rule 3, since we have a suffix link, we will follow that suffix link and set the new active node to this node, which is node 2. The active length and the active edge remain the same. So we have a new active point right there. The remainder is still 3, so we need to add more suffixes. Adding the final character D at that point cause another split, like that. So because of rule 2, we just have another split in the same step. So we need a suffix link right there. Rule 3 now dictates that we change the active node back to the root because we don't have any more suffix link to follow. And the active length and the active edge are unchanged. Adding D at this active point causes another split. So we have another split and another suffix link, like that. The active point will now change back to root D0 according to root 1. And root D0 as the active point and remainder is 1 tells us that we have only one more step to do, that is adding the edge D at the root. And then we're done. The active point is now the root, null and 0, remainder is 0, and it's step 10, and we finish the algorithm right there. So, what did we learn? In each step, moving the hash, or basically the position forward, updates of the leaf node in O1 time. But it doesn't deal with the suffix remaining from the previous step, and also the final character of the current step, because that is also a new suffix. Each additional insert is done in O1 time, because the active point tells us where we need to insert. That is why we have the rules and the suffix link, because those things move the active point for us to the position that we want to, so that we can insert more easily. If during insertion we find that the character that we want to insert is already stored in the tree, we don't do anything, because it is stored implicitly. That is why it's called an implicit suffix tree, because it's already there, so we don't need to do anything about it. We just leave it there, and we will move on and add. If we have the opportunity, we will go back and we will add it in, so that it becomes more explicit. And if at the end the remainder is bigger than 0, which is symbolize that we didn't add in of the suffix, or it is stored implicitly in there somewhere. In that case, we must append the terminating character at the end of the string to signal that it is also a suffix of the string. And though there are many rules in executing the algorithm, we can see that it is linear complexity, because in each step we extend the suffix in O1 or do nothing. If we do nothing, we increment the remainder so that we remember to do it the next time. And because there are n suffixes, it will take O(n) time. That is all for the demo. But from the demonstration, I think we all have the same question. This algorithm is very complicated. How can I implement it, right? So now we will guide you through how to implement the suffix tree in your program. First is the pseudocode. The pseudocode is for people who wants to do to build the algorithm themselves. So those of you who want to try and build the Ukonen's algorithm and the data structure that is the suffix tree, you can read the pseudocode. You can pause right there and read the pseudocode and maybe try a little bit. Next, we will go into detail how to design the data structure. First is the structure of the node. The node have variables so that we can use it in the Ukonen's algorithm. First is the start. The start is the index of the start of the substring of the edge pointing to that node, and the end is of course the end of that of the substring of the edge. But the end is a share pointer because if we want to update all the leaf at the same time, it needs to have the same end. So we need a share pointer. A suffix link is a pointer to another node, as described in the demonstration earlier. And lastly, we need a collection of child nodes that are mapped to using the first character of the edge leading to it. The last line is just a constructor that makes things easier by initializing the node when we know its start and end. Next is the variables and constructor of the class suffix tree. All the variables, all the familiar variables, the string, the root, the active node, active edge, the active length, the remainder, the position. We also need the last created internal node so that we can check if we need to add in a new suffix link or not, and a leaf end so that we can update easily. The last part is the constructor for the suffix tree. We have the text. We add in the dollar sign as the terminating character. Remember, the terminating character cannot be in the alphabet that creates the string. So the string cannot have any dollar sign in it. Here we just use the dollar sign as a terminating character. If your alphabet has the dollar sign, please use another character. It's just a very special character that you don't have in your alphabet. That's fine. The remainder initially set to 0. The active length also initially set to 0. And the position initially set to -1, so that we haven't started the string yet. If the string is an empty string, it is -1. If it has one character, after the first step, it will be 0. So -1 is our special value. And this is the main function. Yeah. It's long, all right. But the implementation of a complex algorithm as Ukonen's algorithm needs to be complex too. You can stop and make a deep dive, look through each line of the code so you understand if necessary. Okay, I think if you had enough time to pause. So we also have the Python code for all of those who use Python out there. Shout out to Python. This is the class of the node and the suffix tree class initialization, and the two-page over in the middle and the right is the main function. Also use extend suffix tree and build suffix tree. This is basically very similar to the C++ code.
Suffix tree are super handy because it can build really quickly in linear time and they are great at finding patterns in string. That makes them a key tool for all such string-related problems, especially in fields like processing and bioinformatics. That great at spotting repeated part of a string, finding palindrome, and answering string question fast. Thanks to all that, software are used in a bunch of cool and practical way. Some of the main applications include bioinformatics. In bioinformatics, software are super helpful for working with DNA, RNA, and protein sequence. Since these sequences are a really long string of letters, software make it much easier to search for patterns, very big and compare different sequences quickly. For example, when scientists try to pair together a genome from a lot of short DNA fragments, software help figure out where the pair match up. They are also great for spotting shared patterns between chains and finding special regions in a sequence. Because they are fast and efficient, software have become a go-to tool in many areas of biological data analytics. The second AI Bell and checking autocomplete. Suffixes are often used to store a several or possible suffix of a dictionary or use the provide input. This structure makes it possible to perform large lookup, which is especially useful for applications because like autocomplete system or spell checker by organizing the data in that way that allow with access to any string. Software can suggest correct spelling or complete work even when only a part of the input is available. For instance, a user begins typing a word, the software can immediately retrieve all dictionary entry that match the current graphic, enabling real-time suggestion and correction. This not only improves user experience, but also enhance the speed and accuracy of the page interface in everything from search engine to mobile keyboard. The third area is data compression. Software play an important role in data compression by helping identify repeated patterns and switching within a file or data stream. Many compression algorithms like RZ, RZ77 and RZ78 rely on detecting the repetition to replace them with the sector reference, effectively reducing the overall size of the data. Software make this process faster and more efficient by allowing quick searching for the longest path of something within input. This helps the algorithm for scanning the entire data every time it looks for a match by organizing all suffix of a string in a command and a suitable way. Software significantly speed up um, the pattern discover process with a key to efficient and effective data compression.
Now, let's examine some programming challenges using sophistry. For the first problem, we are given two substrings S and T. Find the longest common substring between them. This is a classic problem that utilizes the best of sophistry strengths. This is because the common substring of two strings will merge into the same path if we build the sophistry of the string created by concatenating S and T. For the next problem, we are given a string S and we need to find the longest substring that appear two or more times in S. A sophistry solves this efficiently by representing on suffixes in a compact trie, then using a depth first search to find the deepest internal knot shared by multiple suffixes. This knot marks the repeated substring and its depth gives length. This problem is actually similar to LeetCode problem 1044. Here we have two more problems. For the first one, we need to find the longest palindromic substring. This problem is similar to LeetCode problem 5. In this problem, we can try and find the common substring between S and the reverse of S, and then check if it's a palindromic and update if necessary. For the other problem, we need to find the index of the first occurrence in a string, or LeetCode problem 2.1. In this problem, you can build a suffix tree for the haystack and then search for the needle in the suffix tree. If the search fails at any point, you can return -1, otherwise you can find the index needed. To end it up, we want to give some special thanks to the author and contributors of the references cited. Their work has been invaluable in the creation and success of this representation. And not to forget about the assistance from AI such as CS50.ai and ChatGPT. This is the end of our presentation. We want to thank for your time and attention. We hope that this presentation will illuminate the power and versatility of Suffix tree.